Okay. So thank you very much, and thank you very much for the invitation, for being here. It's a pleasure to give this short talk. So I'm going to talk about random interpolating sequences in Dirichlet type spaces. And this is a topic which lies between function theory in spaces of analytic functions and probability theory. So just the idea is to make a quick pass through this scale of weighted Dirichlet spaces that we'll be interested in, discuss about these interpolation problems that we study there in complex analysis, and then impose some probabilistic structure and discuss some theorems on this probabilistic setting. This is what I'm going to talk about is almost completely joint work with Andreas Hartmann, Karim Kelai, and Brett Wick. So just a quick reminder, we're working with this scale of weighted Dirichlet spaces, which we denote by calligraphic D index S. So S is some parameter less or equal than 1. So there are many ways to define these spaces, right? One is to consider functions analytic in the unit disk, such that this norm that I defined here, a norm involving the derivative with this weight, is finite. And this defines the norm of the space. This is equivalent, if you use Parseval's formula, to this norm defined in terms of the Taylor coefficients. So it's just a way.
What is E capital?
Sorry, is there any question?
In the measure. Is
it's the normalized Lebesgue measure.
Okay.
Yeah. Sorry. Yes, and you can, using Parseval's formula, you can write this integral as a weighted L2 norm of the Taylor coefficients, of Fourier coefficients of the function. And this defines a family of reproducing kernel Hilbert spaces, which contains some of the most important examples in the unit disk. So we have the Hardy space for S equals 0, and then on the other side, we have the Dirichlet space for S equals 1 and the Bergman space for S equals -1. And these are all reproducing kernel Hilbert spaces. So you can write an explicit formula for the kernel, which is just this. Sorry. Maybe this is better. Yes, which is given by this logarithm for the Dirichlet space, and this exponentials of the Szeged kernel for other values of the parameter. So now these are the spaces that we consider in this talk. And now we want to introduce some kind of notion of interpolation. So there are many ways one can do this, but we concentrate on maybe the most standard one for this type of spaces. So suppose we have a sequence in the unit disk, and we consider the following, what we call weighted restriction operator. So what this operator does is that it takes a function in this space, and it restricts it on the sequence that we have a priori defined, and it weights by this norm of the reproducing kernel. So why the appearance of this weight here is it's not obvious at this point, but it turns out that it's the most natural thing that you can do. But be careful, because the dust arrow that I put here, it means that it's not a priori clear or even true that this operator is well defined, in the sense that this is always a little L2 sequence. It might happen that for a particular choice of sequence Z, there exist functions which leave the little L2 space. So independently of this, we give our two central definitions for this topic, which first is the following. We call a sequence Z simply interpolating, or SI, if this operator is surjective. So if for any little L2 sequence, I can find the function f in my space such that T of Z, Tz of F equals this little L2 sequence. If even more, the operator Tz is bounded and surjective, we call these sequences universally interpolating. So this is a further requirement which says that any sequence, any function that I restrict in this way, it gives me a sequence in little L2. So these are a priori two different things. Right? One is weaker than the other. Some very quick remarks on the definitions. The boundedness of the restriction operator is equivalent to what we call a Carlson measure condition. So if you define this discrete measure, which is just the weighted sum of some Dirac deltas placed at these points of the sequence, then saying that Tz is bounded is exactly the same thing as saying that the space ds is a subset of L2 of this measure. So in the jargon of complex analysis, d mu z is a Carlson measure. And this is just by writing down the inequality from the boundedness of the operator. And another more subtle, let's say, remark is that when the sequence is simply interpolating, then there exists a bounded right inverse, even though our operator might be unbounded. So this means that I can have a linear, what is called linear interpolation operator. So I can find a function f such that associated to any little L2 sequence, such that it solves the interpolation problem, but the norm also is bounded by some constant, the norm of the initial data, some technicality that will come up later. And another condition, the last one, I promise, which is an implication of simple or universal interpolation, is what is called the weak separation, and it will be quite important for our discussion. So this is a condition that it is implied by interpolation, and it says that if a sequence is simply interpolating, then it must be separated with respect to some ad hoc metric. The metric is what is called the Gleason metric, and the distance between 2 points, this expression, which you can read more easily, is just the absolute value of the sinus of the angle of the two reproducing kernels at the points W. And it says that if a sequence is interpolating in either sense, then it's separated with respect to this Gleason metric. So the distance between any two distinct points is bounded below by some absolute constant. Now, this was a bit abstract, so let's go back to the spaces that we were introduced before. So what is in fact geometrically weak separation in this concrete case? Here there is an important distinction. So when S is strictly smaller than 1, then a weak separation is in fact equivalent to separation with respect to the Poincaré metric or the hyperbolic metric of the unit disk. So there exists an epsilon such that the hyperbolic, this dh will be the hyperbolic metric. Distance of 2 points is greater than epsilon for any I different than j. This is not the case for the Dirichlet space when S equals 1 exactly. The separation condition becomes a little bit different, and it can be described in this way. It says, maybe you can see it in the picture more clearly, that if I fix a point zi in the sequence, there exists a hyperbolic disk of radius comparable to the distance of zi to the origin, this quantity here, such that in this disk there are no other points of the sequence. So this is a much stronger separation condition. So some examples, this type of interpolation was first studied by Carlson and Shapiro and Seals in the 50s, 60s. And I mean, it turns out that universal, in the hard space, universal and simple interpolation are equivalent. And they are further equivalent to the weak separation, which is in the case is pseudo hyperbolic separation, plus the Carlson measure condition on this measure, this associated measure that we have. For the weighted Dirichlet spaces, we know that this equivalence still continues to hold, universal interpolation is equivalent to weak separation plus the Carlson measure condition. Although simple interpolation is a different thing for the at least for the Dirichlet space for when s equals 1, and we don't know what happens in between if simple interpolation still implies universal interpolation. So that was all stuff from complex analysis. Now we want to put some to randomize the problem. So my motivation for these definitions that will follow was in fact to somehow guess which type of sequences are generic and more which is the typical behavior of a sequence. And of course, to do this, you have to somehow randomize the selection of your sequence. So there are a lot of ways to do this, and the approach that we followed is the simplest one, and it's called Steinhaus sequence. So what do? You take some theta n, which is just independently uniformly distributed random variables in 0 to pi, and you fix some deterministic sequence of radii, which will be positive numbers between 0 and 1. And then you define your random sequence in the obvious way. Theta n will be the argument, Rn is the modulus. This is called Steinhaus sequence. So notice that, in fact, these conditions that we had before, being interpolating, being separated, being Carlson sequence, are all tail events for this Steinhaus sequence. So the Kolmogorov 0-1 theorem applies. So tail event, here I have the exact definition, but intuitively, of course, it means that it does not depend on any finite portion of my sequence. It only depends on the eventual behavior of the sequence. And so what we expect to find is some condition, which would depend on Rn, of course, because Rn we fixed beforehand, which tells us when this event happens with probability 1, and that's when this condition fails, the event will almost never happen. So we're after these conditions. This, to formulate these results, is quite convenient to introduce this counting function, let's say. So this capital N, it counts the number of points that, to say it in a different way, have hyperbolic distance pretty much n to the origin. So this problem was a little bit studied already, at least for the Hardy space. And Khosran had proved that the Steinhaus sequence lambda is almost surely hyperbolically separated, so with respect to the Poincare metric, if and only if this summability condition on the square of the counting function holds. This is a bit of an interesting condition because there is a square on the counting function, which is, for me, it's a bit, there is some variance here. Then Rudowitz proved that this condition is sufficient for the associated measure to be Carlson. So in fact, if you use then the deterministic results, you can see that the sequence is almost surely interpolating for the Hardy space. Remember that in the Hardy space, we have no distinction between universal and simple are the same thing. Is interpolating for the Hardy space if and only if this condition holds. And if this condition fails, it will be almost never interpolating, of course. So in this direction, we have first a small improvement of the result of Rudowitz, which says that in fact, you can replace this 2 by any beta strictly greater than 1. And still, then the associated measure is almost surely Carlson. And in fact, we proved that what is called the Blaschke condition, which is the one you get if you put beta equals 1, is not anymore sufficient. So in some weak sense, our result is sharp, but there is still room for improvement in this.
Nikos, it is not sufficient, but it is necessary, right?
It is necessary, yes.
It is necessary, right.
Yes, it is necessary. So now we study the rest of this scale of spaces. Here we find this strange behavior, which I will discuss, which is in the middle point of this range. So in this D1.5, the behavior changes. So let's first see what happens in the range between 0 and 1/2. So when we are, let's say, closer to the Hardy space in some sense. Then, surprisingly enough, universal interpolation, the Kolmogorov 0-1 law for universal interpolation is given by exactly the same condition. So if this sum converges, it's almost surely universally interpolating. And it's interesting to note here that even though we don't know that if there exists some simply interpolating sequences which are not universally interpolating, at least on this probabilistic setting, there is no difference. You can replace this UI here by SI and you have exactly the same theorem. So UI and SI, at least probabilistically, are the same in this setting. And then in this half, which is closer to the Dirichlet space, we have a different behavior. So first of all, notice that when S is greater or equal than 1/2, so this middle point goes to the belongs to the Hardy to the Dirichlet space behavior. So in this half range, the Kolmogorov 0-1 law changes, and it depends, in fact, on the exact value of the parameter. And furthermore, it's not a condition on the variance, if I might say. It's a condition, some ability condition on the sequence. So in fact, universal interpolation is equivalent to the convergence of these distances of these points to the boundary, to this power. And the same thing, it continues here. Simple interpolation is the same as universal interpolation, at least probabilistically. We don't know in the deterministic setting what happens. I should notice that this condition appears already in the literature in the work of Carlson, and it's a sufficient condition for a sequence to be a zero sequence for the Dirichlet space DS. Zero sequence, it means that there exists a holomorphic function which vanishes exactly on this sequence. So as a corollary, we get that Steinhaus sequences are almost surely universally interpolating, if and only if are almost surely zero sequences, which is a much weaker condition in general. And now let's go to the last case, which is the other endpoint of the spectrum, which is the Dirichlet space S equals 1. Here we have a theorem which appears identical. So it gives the characterization of universal interpolating sequences in terms of the summability condition, which this summability condition is known also as Shapiro-Shilds condition. And in fact, the strange thing that happens here is that although we know that deterministically there exist sequences which are simply interpolating but not universally interpolating, still probabilistically in the Steinhaus sequence setting there is no distinction. Almost surely are the same thing. So also about this result, it looks superficially the same as it gives this Kolmogorov law in terms of a summability condition, but there exists an important difference. Remember that weak separation, which was a consequence of it was a necessary condition for interpolation. It is very different in the Dirichlet space. So if one wants to prove this theorem, it has to also prove a Kolmogorov 0-1 law for weak separation. Here, I remind you that for S smaller than 1, weak separation is Poincare metric, separation with respect to Poincare metric. And for the Dirichlet space, you have this stronger condition. So that is what our last theorem says. It gives a Kolmogorov law for weak separation in the Dirichlet space. So this time is of a different nature. It's a growth condition. And it says that the Steinhaus sequence is weakly separated for the Dirichlet space, almost surely, if and only if the number of points that have hyperbolic distance at most n to the origin. So you take a hyperbolic disk of hyperbolic radius n, and you count the points in there. It grows at most like 2 to the gamma n, where gamma is strictly less than 1/2. Okay. So that was probably, I am not going to discuss much about the proofs. I just wanted to tell you that this is our preprint where you can find these theorems. And in fact, very recently, the same problem, it was studied by some other people in this preprint in the sequences in the unit ball and in the polydisk. Thank you very much for your attention.
Thank you very much for the talk. If anyone have questions or remarks, please.
So, excuse me, Nikos, but you mentioned briefly several dimensions, but from the little you said about proofs, it seems that there is no, so several dimensions and one dimension, there is no, it's not particularly different, or am I wrong?
Okay, there is a difference. I have not yet read the paper which generalizes these results in several dimensions, but there is a difficulty which I can see, which lies in the in some estimates for capacity, so logarithmic capacity. In fact, what we use is that if you have a set of fixed measure in the circle, then it has the minimum capacity if it's an interval.
If fixing measure and minimizing capacity.
Then the set which minimizes capacity is an interval. And we use this in the proofs, which I'm not sure how you can obtain an analog in the unit ball for Bessel, non-isotropic Bessel capacities, but probably they found some way around this problem.
It's not true? Wait, in several dimensions, it's not true, you say?
I don't know if it's true or not, because you have some non-isotropic capacities, so I don't know if it's...
I think it is.
I think it is.
I think, okay. We think it is.
I have to check, but I think it is because it's...
okay.
Kind of isocapacitor inequality.
Yeah, it may very well be true. So
yeah, because the kernel is the reciprocal of distance. I think everything works. Pretty much.
Yeah. Okay.
But I have to read the paper of Diane and Brent.
Yeah. So I mean, it might very well happen that some similar proof goes through, but I don't know if they exploited some alternative way. I don't know. In the polydisk, it seems that there are much more open problems from what I've read.
Okay. Thank you very much.
So any more questions? If there is none, then we just have a 5-minute quick break.
Thank you.
Так.
Слушай, это самое, ты
Well, okay, I guess we can proceed. The next speaker is Pierre Lazag from l'Université d'Aix-Marseille, and the title is A Law of Large Number for Local Patterns in Random Plane Partitions.
Okay, thank you very much. So do you hear me, and do you see my screen or not?
Yes.
Yes, perfect. So thank you very much, and thank you to the organizers. I'm very happy to speak and to tell you a bit about part of my work. So it will concern a law of large numbers for local patterns in random plane partitions. So, and it will involve determinantal processes. And so let's start. It does not work anymore. Okay. Yes. So first of all, I will present the model, so the random plane partition I consider. Tell what are the limit processes. So these are theorems of Kunkov and Dirichlet. Then I present the results about the law of large numbers and tell somewhat about the proof. So a plane partition, so it's a double array of integers, which is of non-negative integers, which is finite, which means you can sum them, and that is non-increasing in both directions. So these are the two conditions which are written here. I consider a geometric rate on the set of all plane partitions. That is, they depend on the parameter q, which is in 0, 1, and is proportional to q to the volume of the partition, so to this sum. And c is just the normalizing constant. So I told you at the beginning that it would be about determinantal processes, because yes, so you can associate a configuration on the lattice E, so Z times 1/2 of Z, to a partition. So the formula is like this, and don't worry, I show you a picture and everything will be clear now. So this is a plane partition. You consider a quadrant here in R3, and for example, if you have this partition, you put four boxes here at this corner, then the 3 here, 3 here, 2 here, etc. And you project it in a natural way on R2 on the plane, and you put particles, so the blue dots which are here, on the top facet of each box of your partitions. So in that way, random plane partitions are point processes, which means random configurations of points on the lattice E. So tell me if nothing is not clear, ask questions, feel free. Okay, and yes, as announced, there's a theorem which I will not prove at all by Okunkov and Rishitikin. We say that this point process, so the image of the geometric rate on plane partitions by my map sigma is a determinantal process with this kernel. So this kernel is given by double control integrals. So here S is in Z and X is in 1/2 of Z. So these are the coordinates in the space E in the lattice. The function phi is well, it's a function which is expressed as a ratio of sort of Q deformations of Pochhammer symbols. So the expression is here. It is not very important, but just to say that it has some singularities, and the number epsilon is chosen in such a way that we count these singularities to evaluate your kernel. Yes, those you take the plus sign and the minus sign here when this time is, so this first coordinate is bigger than the second one, and the minus sign otherwise. So let me just remark that this kernel is not symmetric. It does not define a Hermitian operator, and for these kinds of determinantal processes, there is not a lot that is known about them. Okay, so now let me tell you what the limit processes are. So the regime we are interested in is as q tends to 1, and the convenient parameter will be minus the logarithm of q, which is r. So you write q as exponential to the minus r with positive r, and you let r tend to 0. So you have a local limit behavior in your random plane partitions when you look at a specific limit shape. So this is the formula for the limit shape, and just let me go back to the picture. I show you a little bit. So it looks like this. You have a curve here, one here, one here, and the form A is the inside of which is delimited by these curves. So when you have parameters in this limit shape, you can define a new kernel, which will define the translation invariant point process. So it is this time given by a simple integral on an arc. So the arc, it goes from a point z bar to its conjugated z, and it's defined as they are defined as the intersection points of two circles. One centered at 0 and of radius exponential to the -2/2, and the other, this one, centered at 1 and with radius exponential to the -2/4 minus chi/2. And well, since Tokai are in this limit shape, these circles have intersection, do intersect. And the limit theorem says that if you look locally around Tokai and you scale it by a factor 1/r, and you look at the local behavior around this point, so you add a little to Ti, Hi, which are fixed, then you obtain a non-trivial limited behavior, which is a determinantal process with this limiting kernel. So later I will say precisely what it means in terms of just probability. Okay, now let me explain the law of large number. So some notation. If I consider any set of distinct points in the lattice E, I define this random variable, so the indicator of M of a random partition, of a partition, plane partition pi. So I say it is 1 if the configuration corresponding to pi contains this set M, and it is 0 otherwise. So since we have determinantal processes, this translates into this following. So the probability of finding the set M inside the configuration given by pi. This is so the expectation of my random variable I defined above. And this is given by the determinant taken at the coordinates of the set M. And the same for the limiting process. So this is a determinantal process. Here the configuration does not more correspond to a plane partition, but it's still a configuration on E, and the probability of finding a set M is the determinant of this translation invariant kernel at these coordinates. And the limit theorems translates into this fact. So you ask yourself the question of, you look at locally at a position Tokai in your big plane partitions, you scale it. So you look at right away at R-1 around R-1 Tokai, and you ask yourself if it contains M, and precisely you arrive to this limiting process given by this translation invariant kernel.
So, excuse me, Pierre. So
yes.
the first PQ lives on finite configurations, and P tau he lives on infinite configurations, on stationary configurations.
Yes. So PQ does not exactly live on finite configurations, but in
semi-finite, on semi-finite.
Semi-finite, yes.
Semi-finite. Thank you very much. Yes, of course, semi-finite. Yes, that's right.
Yes, and these are stationary configurations, is the limiting one. So, and the theorem says that if I take any compactly supported continuous function f from the plane to R, and any finite set M, I consider this random sum. So it means I will evaluate my function at RT, RH if I can see the pattern M around the position TH. All the TH are so in the lattice and in the scale limit shape. So the absolute sum is finite because F has compact support. And each time I see the pattern M around a position TH, I evaluate my function at point RT/RH, and I scale all the sum by a factor R/2. So and R will go to 0. And so this is a law of large numbers. So the limit exists and is a constant. And this is you average the function F on the limit shape A. And you weighted your give a weight to your average, and the weight is the probability of finding M in the limit process, and you average with respect to the parameters of the limit processes. Okay, and this is a convergence in probability under P to PQ, where Q is e to the minus R. So this just means that for any epsilons, the probability is that the left-hand side minus the right-hand side is bigger than epsilon and goes to 0 as R tends to 0. Okay, so how do you prove this sort of weak law of large number? So first we prove that the expectation of the left-hand side goes to the right-hand side. And then you have to control the variance and to show that the variance of the left-hand side tends to 0. And by the Chebyshev inequality, you have the weak law of large number. So here the difficulty is in the second point when you want to show that the variance goes to 0, because as I said, you have a non-symmetric kernel, and you cannot compare variances with sort of Sobolev norm as because you don't have as far as I know, you don't have a natural way to associate function spaces to this kind of determinantal processes, and so you have to do something else that Sasha did this morning, for example. So let me first briefly show the first point. This is just the limit theorem by Okunkov and Rishitihin. So you take the expectation, and then you can move the expectation to the right because the sum is finite, F has compact support. And so the expectation with respect to e to the minus r here, you can replace it as the limit, the expectation with the limit process, but with parameter rt and rh, and you have some rest that you control, which is of order r. And this is it, because here you can recognize this sum as a Riemann sum for the limiting integral, yes? Because it's just, you evaluate your function in some scale lattice, and then the lattice goes to the whole plane. And this is because the function f is continuous, the Riemann sum converges to the integral. Okay, so now we want, so the variance, you can write it like this, and you want to show that it goes to 0. So the way so this is just by developing the square, yes? That's which makes you arrive to this expression. So in order to do this, we will have to control these covariances here if you want. And we will control them depending on the fact that if the point T1, H1 and T2, H2 are far away from each other or not. So, and this is the main lemma, which gives the control of these covariances. So you fix any finite set M, a compact set K in R2. So you think of it as it's a support of F. And for any parameter alpha, there will exist a constant such that for sufficiently small r, if your parameters live in the compact, the limit shape, and the scaled lattice, if they are far away enough, so this is the condition to be far away enough. So the distance, this is sort of a distance between them, and it has to, you can give a precise control on this distance. Then the covariances will be smaller than, not exponential in R, but almost exponential in R, but will be smaller than exponential minus R to the alpha. So this to the minus alpha, so I don't see what is written here. And here you have a precise control about the different tau you have. And when they are equal, the things are more involved. And you have here a linear control in R, not an exponential one. And again, you also have a control depending on the distance between the parameters. Okay, so this is now the lemma I want to prove, and I don't know what time is it. Yes, I still have time. And first of all, I explain how the limit theorem works, and it will give us hints in order to prove this control on the covariances. So I remind you, this was the integrand in the kernel given by the double control integral for the original point process PQ on plane partitions, and we have an asymptotic result for it. And so the function S, I don't write the precise expression, but just some properties. So first of all, because you have this asymptotics, so the kernel is equivalent to this quantity. And here, in order to count singularities, you integrate not on the unit circle, but on this circle. And what we know about this function S, and what will be important, is that its real part is constant on this circle. And the function S has two critical points, which are complex conjugated, and these are precisely given by the one which will give us the simple integral for the limiting kernel. And we also know the sign of the gradient of the wheel part of S on this circle gamma tau. And we will be able to deform the contour. So let me show you the deformation of the contour. So, and yes, just something I did not say is that here, so for example, the modulus of Z is bigger than the modulus of W, for example, and you have a residue at Z equals W in the prelimit kernel. That then, for example, you want the real part of what you have in the exponential to be negative. So since we know the gradient of this real part, let's say it goes in this direction on this arc, and in the other direction on the other arc. And so if you choose the W to be here and Z to be here, so the real part of the difference between both will be always negative, except at this critical point. So we deform the contour in this way, but here since I deform the contour, I do not integrate the residue at Z equals W anymore, which gives the limit behavior. So here is written what I told you. So the real part will be negative, except at the critical point where you have equality. And if you integrate the residue at Z equals W, you obtain the limiting kernel. And this is the end of the proof of the limit theorem. So now what we do for the covariances. So first remark that this condition I gave, so to be far away enough, it means that these ensembles, so this set of points, this finite set of points, are disjoint. And so this is important to know why they are disjoint, because now I can express the covariance as a sum, and each term of this sum will contain a factor of this type. So look at here, you have a first argument which is in tau1 chi1, the second one in tau2 chi2, and for the other factors the arguments are reversed. So the first argument is tau2 chi2 and the second one is tau1 chi1. And so in a way we symmetrized the problem here, because the kernel K was not symmetric, but this expression is much more symmetric. And just let me explain why we have factors of this type, and this highly relies on the determinantal structure of the process. So let me explain it to you. So since this set are disjoint, this expectation, so this is a determinant. So this is an alternate sum of size 2m, because they are disjoint. So the union of the sets is of size 2m. And this alternate sums is when you develop the determinant, they can be of two types. So you can consider permutation, which fixed the first part and the second one, and you have other one when you consider points in your matrix which are not in the main block, if you want, but in the off diagonal blocks. And what happens is that if I take the sum over all permutations, which leaves these two diagonal blocks invariant, well, this is just the product of the determinants. So this is the product of the expectation. So yes, because this is the determinant of this times the determinant of this, you just consider permutation which fix these two diagonal blocks. So when you look at the covariances, you subtract the sum over all the partition which lets the diagonal blocks invariant. So you are left with the permutation of the second type. And the permutation of the second types, this is precisely if you consider one point here, you have to consider one point here. And so this is precisely the kernel evaluated at two different points and symmetrized because you take the product of both of them. So, and this is the claim I gave you before when I say that you have factors of this type at each time in the covariances. And why did we symmetrize the problem? Because now, okay, the limiting function S you have in the integrand. If you just consider one thing, one factor, you won't have something like this. And here you have different parameters. So how to deform the contours, this you don't know. But now you can regroup the function S at Z with the first parameter, with the function S at W prime with the first parameter, and the same thing for the other. So, and this is how the deformed contour will look like. So for example, here you have the function S depending on Z, and here you will have the one depending on W prime. So with the parameter, so no, here with W, sorry, and here with the W prime, etc. And in this way, deforming the contour like this, the will part of this sum and difference of 4 terms will be negative. And when you consider different times, so different position tau, different coordinates tau, this does not affect the value of the kernel, because here, well, here you have Z, you have a residue as Z equals W, but W will always be here. So in another circle, so you keep counting the residue. And so I have the integral of 1 over R with something which has negative will part except at the critical points. So this, you don't have an exponential decay of the correlation in 1 over R, but something a little bit less than an exponential decay. And here, so I just the tau1 minus tau2 squared just come from this dominator, because Z lives on the circle gamma tau and W on the circle. So gamma tau1 and gamma tau2 for this one, and just within inequality you obtain this thing. I don't know how much time do I have anymore, maybe 2 minutes. So for the case when you have equals parameter for the first coordinates, things are more involved, because now you are let on the same circle, so you have to integrate the residue and to control them, and you control them with the other parameters, so with the parameters in space, so the chi1 and chi2, and just so let me skip this, and just for the technique, so now you have to integrate the residue here and here, and so the equivalent of what we integrate is in W 1 over R chi2 minus chi1, and just integrating by parts. So if you integrate this, you obtain this factor here, and another factor here, which comes from the deformation of the contour. And since we have a product of all of them, these exponential factors simplify each other, and you are left with this asymptotics. So yes, thank you very much. Is somebody here?
Yes, but the chairman seems not so much.
Yeah. Maybe.
Okay, but we will take power in the hands of the people and just.
Oh, excuse me, I'm here.
Okay. So, when we say about power in the hands of the people, the government wakes up immediately.
Okay, yeah. So we have now a 4 minutes break. And
no break, but there are questions. The government wakes up immediately and says something inappropriate. So, okay.
Sorry.
So, excuse me.
You couldn't hear this part too. I was saying about questions. Okay. So if anybody have questions, please.
Okay, good. So Pierre, excuse me, you said words limit theorem, but in fact, what you said is law of large numbers. But precisely my question is there limit theorem in this? In your result, in your main theorem, it's essentially law of large numbers, but is there limit theorem?
You mean like the central limit theorem?
Or not?
Or not? I don't know.
So maybe this question makes sense.
Yeah.
Because these are version of sign process, maybe it's possible that there is even some limit theorem with finite variance. Just not obviously it's determinantal, so there is central limit theorem of Soshnikov, the general one, but maybe there is even more specific limit theorem for just homotetized random variables with finite variance, something like this, like for sign process.
What do you mean? With a discrete sign process?
Continuous sign process. But it's also true for discrete. But when you have a convergence to normal distribution of random variables with finite variance, some sort of Segur theorem.
Okay, yes, I see. It's a good question. I don't know.
Okay.
I don't know, but no, I don't know.
Maybe we can discuss it later.
We can discuss this later. But just to mention, even the strong law of large number will be complicated because.
Игорь, по поводу вашей терминологии, закон больших чисел тоже предельная теорема.
So I translate. So the law of large numbers is also a limit theorem. Certainly. It is so much true that in fact in my habilitation thesis, it was called something like limit theorems for this and that, and some of the limit theorems was in fact ergodic theorem. So I not only I know this, but I took advantage of it. But yes, but I mean limit theorem in the sense of convergence in convergence to non-trivial distribution. So convergence of non-trivial, non-delta distribution.
Yeah. We have to check, but so even these kinds of law of large number do not really exist in the literature as far as I know. So the techniques we have to employ for central limit theorems, it is still quite mysterious for me.
But something like Segur theorem, something in the spirit of Segur theorem, one would think. Okay, maybe we can discuss later.
Yeah, but nothing is symmetric here, so Segur theorem. I don't know.
Okay. So it was question. It was just question.
Yeah. Thank you.
So okay, if nobody else have questions or comments, thank you very much, Pierre. It's been a very interesting talk. And we can now proceed to the last talk of today's session. Tatiana Moseeva from St. Petersburg State University will deliver a talk on random sections of convex bodies and the distribution of the volume of weighted Gaussian simplex. Tatiana?
Yes, I'm here. Good afternoon.
You can share the screen now.
Can you see my screen?
Yep.
Yeah, okay. Oh, wait a minute. Are the slides changing?
Yes. We see everything. Everything is fine. Yes.
I guess we can start. Well, first of all, I would like to thank the organizers for giving me the opportunity to give a talk here. It's been a great pleasure to attend such a great conference. Now let's start. Today, I'm gonna talk to you about two topics. First, we're gonna talk about some connection between the distance between two random points in some convex body and the length of the random chord of this body. This part will have actually two parts. First, we'll talk about the Euclidean case, and then we'll switch to the spherical case of the problem. And then, if we have some time left, we're going to talk about the distribution of the volume of weighted Gaussian simplex. Well, let's start. First, let K be a convex body in d-dimensional Euclidean space. Then we can consider the following two random variables associated with this convex body. First, let's take two random points independently and uniformly in K. Then by delta, we will denote the distance between these random points, and delta will be the first random variable we are interested in. Secondly, we can intersect our convex body with some random line. By random line, I mean that we take the set of all lines intersecting K and then choose one of them uniformly with respect to our measure on this set. By sigma of K, we will denote the length of the intersection, and we'll call the intersection a random chord of K. So now we have two random variables, and we want to know how these random variables are connected. First, let me say why there are any reasons to believe that such connection exists. In 1961, Kingman showed such an equality that you can see on the slide. And let's look at it precisely and understand what's written here. The left-hand side is up to some constant, just the pth moment of the distance between two random points. And the integral in the right-hand side is again up to some constant, depending on some properties of K, is just the p plus d plus first moment of the length of the random chord. So actually, Kingman showed that the pth moment of delta is up to some constant equal to the d plus p plus first moment of sigma. What does it mean? Since both our variables are bounded, we can conclude that the distribution of delta is defined by the distribution of sigma. So we want to find maybe some more explicit expression for one variable in terms of the other variable.
Excuse me, Tatiana, I'm a little bit confused by your notation. What is mu d1?
Oh, yes, thank you. I forgot to tell about that. Yeah, here we take the set of all lines intersecting K. Mu d1 is just the higher measure on this set. So this is actually
But lines passing, through the origin, not necessarily.
No. We take the affine Grassmannian.
Okay, so it's higher measure and affine Grassmannian. Okay, perfect.
Yes,
thank you very much.
Yes, thank you for this note. That's actually quite important. So in planar case, in 2015, Dirichlet and Karanian showed that there exists an explicit formula that expresses the cumulative distribution function of delta in terms of the distribution function of sigma. And our main result generalizes the result of Dirichlet and Karanian to the case of arbitrary dimension of our space. So first, let's give some notation. By f delta and f sigma, we will denote the distribution functions of delta and sigma respectively. And the main result just says that, again, there is an explicit formula that expresses the distribution function of delta in terms of the distribution function of sigma. Here, the distribution function of sigma, f sigma, is just in the last integral. This may be scary, I'm sorry, but the main point here is if we know the distribution function of sigma, that's maybe it's not quite difficult to calculate the distribution function of delta. If we differentiate each part of this equality by t, we can find the expression for the density of the distribution function of delta, again, in terms of the distribution function of sigma. Let's also note that Kingman formula that we mentioned earlier and Karanian's result for plane can also be obtained as a corollary of the main result. Now, let me say that the main instrument in proving the main result.
Can you go one slide back? Is it immediate that Kingman formula is corollary of your main result?
Well, you should just integrate the power of t using this formula, and maybe in 2 pages maybe one, you can get this. It's not immediate, it requires some calculation, but it's not very difficult.
But F sigma is not some very clear, maybe I again confused by notation. F sigma is what again?
F sigma is just the probability that the length of the chord is less than something, but for F sigma there exists some integral notation, like it's the integral of the set of lines where it's the section is less than something. And if we actually, I don't have the such derivation of the Kingman formula in the slides, but if we just substitute the power of x in and integrate this thing, then some, I don't remember correctly, but some integral equalities arise where the integral of F sigma just turns into the moment of chord length. Maybe if you're interested, I can later maybe show you or send you the derivation.
Yes, thank you very much.
Okay, thank you for this question. Now, yes, the main instrument in proving was Blaschke-Pitcairn formula. How does it help us? What Blaschke-Pitcairn formula is? Let's assume that we have some non-negative measurable function of k+1 arguments in Rd, and we want to integrate this function. Then what can we do? Let's fix some k-dimensional affine plane and integrate our function multiplied by the volume of convex hull of these points up to some power over this k-dimensional space. Here, that's actually the power of E is k+1. I'm sorry, that's a misprint. And after integrating over this k-dimensional space, we just integrate over all k-dimensional spaces. So it's like we change the coordinates, and the d minus k power of the volume of the convex hull is just the Jacobian of this change, this transform. Using Blaschke-Pitcairn formula, we proved the previous result. And it turns out that there exists a spherical analog of Blaschke-Pitcairn formula. And it looks like this. Actually, it looks a lot similar. If we have, again, non-negative measurable function of k arguments on a unit sphere, then to integrate it, we again just choose a k-dimensional, now linear space, integrate over the intersection of this space with sphere, and then again integrate over all k-dimensional spaces. Let's notice that the Jacobian of this transform is similar to the previous case. It's just now we take the convex hull not only of our points, but of our points and the origin. Knowing that there exists a spherical analog of Blaschke-Pitcairn formula, there was a hope that we can find the analog of the previous result in spherical case. It turned out that this analog really exists. Okay, now let K be a spherical convex body. By spherical convex body, I mean that it can be obtained as an intersection of unit sphere with some convex cone Rd, and this cone should not contain lines. Now let's say what analogs of delta and sigma are. By delta, we will denote the spherical distance between two random points, again chosen uniformly and independently in K. We can also say that delta angle between two random lines intersecting K, and these random lines again should be chosen independently and uniformly from one-dimensional Grassmannian linear. Now we need to show what the analog of a chord is in our case. Well, let's just say that some chord of K is an intersection of K with some two-dimensional linear plane. And random chord of K is just an intersection of K with a two-dimensional linear plane chosen uniformly from the set of the all two-dimensional linear planes intersecting K with respect to our measure on this set. And by sigma, we will again denote the spherical length of this chord. I hope I'm not talking too fast and it's possible to understand me. Now, the main result says that again, there is an explicit formula that expresses the density function of delta in terms of the distribution function of sigma. I also wrote here the result of the previous case so that you can see that these formulas look quite similar. So here we change some constants and instead of the d minus first power of x, we use d minus second power of sign of the argument. Also, I think I might say that what kappa and omega mean here. Kappa d is just the volume of d-dimensional unit ball, and omega d is surface area of unit sphere in RD. I'm sorry I didn't say that earlier. So as you can see, the formulas are quite similar. I also have to say that
can you comment a little bit on the difference between this? Can you unfortunately it's difficult to follow in slide presentations. Can you kindly go back to your result for Euclidean case?
Euclidean case, density function is just at the bottom of this slide, yes.
And just the differences, yeah, so in fact, in some sense there is no difference.
No, of course there is difference, but you see the dependence of F sigma, for example, is the same. We just integrate it over the interval from 0 to the argument.
Mm-hmm. And what about Lobachevsky plane?
Yeah, we haven't thought about that.
It's natural to conjecture that instead of sine, you will have hyperbolic sign.
Yes, after Euclidean and spherical case, there were thoughts that maybe we should try about a Lobachevsky plane, but we haven't done that yet. So,
but usually, I'm sorry, usually the ansatz is proof of your result for sphere. You just substitute square root of -1. You just erase square root of -1 in all trigonometric functions, and you obtain proof for Lobachevsky plane. Excuse me for such naive remark. No, it doesn't work like this.
Yeah, that sounds great. Actually, I should try that. Thank you. No, actually, it's just that we thought of the sphere and then didn't try to do anything for the Lobachevsky plane and left it for later. Okay. And now I guess later came. Yes, thank you. That sounds great, actually. We'll try that. Yes, as I was saying, if you remember, in the Euclidean case, we also had the expression for the distribution function of delta. In the spherical case, again, there is an expression for the distribution function of delta in terms of the distribution function of sigma, but there are some functions in this expression, like the indefinite integral of the power of sine, which of course can be written, but it can be written as some sum of d addends, and it's not really great to look at. But when we differentiate it, all these bad functions just go away, and we are left with a quite nice expression. That I think is really great. Now, let's also say that if K is a spherical cap of some radius, we can find an explicit form for the distribution of the distance between 2 points. Why is that? When K is a spherical cap, the distribution function of the chord length is actually not very difficult to calculate, because it's easy to see that if the chord length is less than some constant, then this chord just must not intersect some smaller cap of some radius we can calculate. And then as the measure of planes not intersecting some cone is just up to some constant, the surface area of intersection of this cone with the sphere, the measure of these planes could be calculated. And from this, we get the result on the slide. Notice that if D is even, then we can, using the Newton binomial, take this integral and get some result. That does not look actually great. It's some big sum, but in the case of even D, we can find the explicit formula for the distribution of the distance between 2 points without any integrals, just using some powers of sines, cosines, and tangents. If there are no questions for the first part, I'm gonna switch to the second part of the talk. The second part will be about weighted Gaussian simplices. First, let X be a standard Gaussian vector in k-dimensional Euclidean space. Then, by definition, its length is heat distributed with k degrees of freedom. Actually, there is what's the length of the vector? Length of the vector is just the volume of the convex hull of 0 and this vector. So there's a nice generalization of this distributional identity to the case of several vectors. Let's take several independent standard Gaussian vectors in d-dimensional Euclidean space. The number of vectors should not exceed the dimension of our space, so that the convex hull of 0 and these vectors is an L-dimensional simplex. And then the volume of the simplex is up to some constant distributed as the product of independent heat distributed random variables. Here, each k has heat distribution with k degrees of freedom, and all the random variables here are independent. Now it's easy to see if we take not just standard Gaussian vectors, but multiply them on some constants, positive. So we take Gaussian vectors with some positive weights. Then to find the distribution of the volume of weighted simplex, we just need to multiply the previous expression by the product of all weights. That's quite easy to see. But if we decide to remove the origin, the problem becomes more subtle. What's going on? In 1971, Miles showed that there is an explicit expression for the moments of the volume of Gaussian simplex without origin. Here, the simplex is not weighted, so we just take the standard Gaussian vectors as the vertices of our simplex. Then, using the explicit expression for the moments of heat distributed random variables, he concluded that using the method of moments, we can find such an distributional equality. Although Miles didn't prove the correction of the using of method of moments and just concluded without any proof. Let's also note that in case of the simplices without origin, the weighted case does not follow from the unweighted case, so simply as in the case with the origin. So in 2020, Julien Renton, Forling, and Dmitry Zaporozhets found the explicit expression for the moments of weighted Gaussian simplex for any positive weights. Again, knowing the identity from the previous slide, authors concluded that using the method of moments, again, we can find the distribution of the volume weighted Gaussian simplex. Although they did not need that result in their work, so they did not prove it, and also suggested that there is a way to find the distribution without calculating the moments. So the goal was to find this proof, to find the proof that did not need calculating the moments. And the main result is that the volume of the weighted Gaussian simplex is again up to some constant that depends on the weights, equal to the product of L independent random variables. Each of them is Hugh distributed with I'm sorry, with some number of degrees of freedom from d minus L to plus 1 to d. I think we should say something about one important step of the proof, because, well, this fact seems not so easy to understand, but it's quite interesting, I think. So let's, the proof uses the induction from d to 1. And when we are proving the case of L less than d, we consider the affine hull of our vectors. With the probability 1, it's a affine plane of dimension L. And then we can project it to the linear plane of dimension L. And so the auxiliary result that we used says that this L-dimensional linear plane is uniformly distributed over the L-dimensional linear Grassmannian and is independent of the volume of convex hull of our points. It slightly reminds us the main property of the Gaussian vectors. So as you all know, if we take a standard Gaussian vector divided by its length, then we get a vector that is uniformly distributed on a sphere and does not depend on the length of our vector. And here is something that's a bit similar. We take an affine hull, take it, the linear plane that's parallel to it, and this plane, again, is uniformly distributed and does not depend on the volume of the convex hull. This fact may be proved similar to the fact about the length of the standard Gaussian vector. We just take two functions. One of their one function has this linear plane as argument, and the other function has the volume of the convex hull as an argument. And then as we integrate it and substitute some different functions, we just get this result. So it's not very difficult to show, but I think it's quite interesting. I guess my time is up. So thank you all for your attention. Any questions?
Yes, thank you very much. If anyone has questions, please ask.
А можно на страницу 17 еще раз?
Да, конечно.
Просто вот я не очень понимаю. Вот эти сигма, их же, грубо говоря, их можно сделать размерными. Казалось бы, размерность левой и правой части должна совпадать. А почему она как-то вот
так, хорошо,
не совпадает?
Давайте подумаем. Хочется размерить сейчас. Давайте поймем, что-то здесь. размерные, то у нас получается плюс первая степень.
Нет, почему? Все хорошо с размерностью.
Почему?
Да? У меня что-то
Потому что если взять или растянуть все сигмы в одинаковое количество раз, то сократится справа и слева растяжение.
Так, слева будет там в А в степени L плюс 1. Вот если в А раз.
So I provide a brief translation. The question is about the dimension count for this formula, and the discussion is whether it works or not. So the discussion has the form yes, no, yes, no. So what is the final result? Is it correct dimension count or not?
Well, Pavel thought that everything is correct, but
okay. Okay. Natasha, do you agree?
I believe.
Okay, that's great. Any more questions?
Questions, remarks? Well, if no one else has questions or remarks, I think I can close today's session. The conference continues tomorrow at midday with a lecture by Professor Elena. Okay. The conference continues tomorrow at midday with a lecture by Professor Elena Yarovaya on branching random walks. On behalf of this conference and on my own behalf, I once again wish you all a Merry Christmas and hope that next winter the conference will be held offline in St. Petersburg. Thank you very much.
I also hope so.